All right. Can we do a different type of problem, Jake? We just did 2 of these. I mean, I can do this one. It's pi day. But I would like to move on to a different type of problem. All right, last one. So 115 pi over 3. I'll take a look at your notes. Okay, so 115 pi over 3. Okay, sine 115 pi over 3. Okay, so Jake, in his notes, kind of big, another way to find equivalent. He says the reference angle is pi over 3. So I guess I'm assuming that's like because you're isolating just with the fraction, right? So you're saying it's like 115 reference angles, right? Where the reference angle is pi over 3. Right. So kind of big. Another way to find equivalent angle, divide numerator by twice the denominator. Our remainder equals the new numerator. Okay, yeah, so that's... I'm just trying to think if that can go wrong somehow, but I guess that's correct, but I'm unclear about the other one, why you got... So what was the other one? I think it was like negative 17 pi over 6 or something, yeah. And then you said do twice the angle. So you had 12. And you had to divide 17 by 12. Negative 17 by 12. By 12. Get remainder negative 5. Or I guess positive. Oh, okay. So you get positive remainder, but it's negative. Is that how you got negative pi over 6? That's a little confusing to me. I mean, I guess if it makes sense to you. Okay, so for the positive angles, I think it's both of our methods basically give you the same angle, but for the negative ones, I think you might be getting some sort of reflected angle. But here it works the same. So your reference angle is pi over 3. When you're multiplying the denominator by 2, that's just seeing like how many 2 pi multiples in units of thirds, which would mean, 6 pi over 3. How many 6 pi over 3s are there in 115 pi over 3s? Right? So you're just dividing 115 by 6, and you want to know what's the remainder. So it's like x times 6 plus some remainder r. Yeah, and then in this case, I think it's like, so it's almost 120. So that's like 20. So 19, I think. with a remainder of 1. So this is 19 times 6 with 1 remainder, I believe. Since 20 times 6 is 120, and then so 19 times 6 is 114. 1 remainder. Is this what your notes are doing? Yeah, so you divided 115 by 6, you got 19. Yeah, so that looks all good. Where did you say the remainder is 1 though? I don't see that. Let me increase the size. Another way to find twice the denominator. I don't see where you said the remainder is 1. Oh, okay, I see it now. Remainder is the new. Okay, I see. So 1, so pi over 3, since that's the reference angle. So you get a sine of pi over 3, and then you said sine of pi over 3 is square root of 3 over 2. Okay, perfect. Yeah, that looks good. Nice. Okay. Yeah, that works. That works. It's just with the negative angles, it seems a little weird. With the positive angles, everything's fine. It works exactly the way it should. With the negative angles, I think sometimes maybe you get the reflected angle that happens to have the same sign, but then you got to be careful with cosine because, yeah, I'm not sure how it works with the negative angles, but it seemed like you didn't get the right angle. You had the right sign, but I'm not sure. So, hello, Bistolis, first time chatter. Happy Pi Day. We're doing some pi-related problems or circle-related problems or any type of math problems on the board right now. All right, Jake. No more the sine some multiple of some fraction of pi. We could do other pi-related problems. We don't have to prove this, but there's always the fancy, like, infinite integral, right? I believe, what is it? E to the negative x squared dx? What is this one? Keep walking into a chair. I always forget what the fractions are. Does anybody remember this one? I think it's like square root of something. I don't want to prove this one though. Yeah, this comes up in probability. This is a really cool integral. I guess, so Zach probably likes this one, because this has e in it, and it has a pi in it. So this is another cool integral. I don't know if Zach's still tuned in. It's not obvious what this has to do with a circle in the first place. Like it's really not obvious. Come on, guys, it's Pi Day. Need more chatters. Think. I think it's like square root of, what is it, pi over 2 or? Or is the 2 in the square root? I can't remember. But yeah, this one, this is a famous integral that comes up in probability. I probably have this wrong, actually. I should probably figure out what it is. Is it square root of pi over 2? Why am I... Or is it just square root of pi? I don't remember. I think it's without the square root. No, it's definitely not without the square root. No, there's definitely a square root. There's another integral maybe you're thinking of, which is like a double integral over R2 e to the negative x squared minus y squared. I think that one's just like pi over 2 or something. Or am I getting the over 2 wrong? Is this... So this is basically the square of this integral. It's not obvious that that's true, because basically this is like symmetric. So instead of one axis, now you have two axes, so you just square it, right? So yeah, I think this is the one that shows up without the square root, but I'm not 100% sure, to be honest. Yeah. I don't know. I guess I can hop into the research that I had planned, the research stream, but yeah, I don't know. I'm down to do some pi related problems. Oh, did I ever write the final answer? Yeah, square root of 3 over 2 is correct for the problem, Jake. Alright, it's a little slow in chat. I thought Pi Day would be a little more energetic, but I guess, you know, I didn't really plan on doing problems on the board, so that's probably my fault. Do we have any other cool integrals we want to go over that include pi, or we could compute pi using an integral other than this way? Test your Greek letter scrolling. You mean with the alpha? All the Greek letters? I think I probably only know the ones that are math related, like alpha, gamma, zeta, xc. Yeah, alpha. Can we compute pi using an integral? Or is that just going to be cheating? Oops. Like, for instance, we know pi is the full area, so it should be 2 times this area, right? Right? Right, and we know that this is some integral, right? This we can describe this as a function, right? This is square root of 1 minus x squared. Positive square root. Right, so pi should be 2 times this integral, right? Dx. And from negative 1 to 1. So how do we solve this integral? I mean, we know it should be pi, right? But can we do Monte Carlo with one sample to estimate pi? Is that what you're saying, Kyler? One sample of one substitution. What are we substituting? Probably some sort of substitution, right? I don't think U substitution works though, because we don't have like an X out here. Maybe if we had an X out here, we could do like a U substitution for 1 minus x squared and 1 minus x squared. Yeah, but if I substitute 1 minus x squared, then I don't have an x dx on the outside. So that's not gonna, I don't think that's gonna help. We need some sort of, we need to cheat somehow, use some sort of trig substitution, which maybe we're assuming. I don't think it, maybe it doesn't assume pi, I guess. Maybe, I guess it doesn't. Or does it? Maybe. I can't tell. So yeah, U equals 1 minus x squared. I don't think that works. Unless I'm wrong. I don't know. My chat can call me out if I'm wrong. But I think I know the correct substitution, but expectation of something and replace it by computing a one sample Monte Carlo estimator of that. Yeah, I think I was talking to you about that really quickly. Damn, I need to brush up on my integrals. Yeah, I mean, so do I. That's why I'm even thinking about this. So I think you can do x equals sine, is it? Or does it matter? Because I know 1 minus like sine squared or 1 minus cosine squared should be the other one, right? Does it matter which one I pick? I guess it matters for the when you take dx. So let's just set x equal to sine theta. So dx is cosine theta d theta. So square root of 1 minus sine squared should be cosine squared, right? Oh, yeah, we need to change these bounds. And what are the bounds? What if you change to 1 over x squared factoring this? What? 1 over x squared? So if the bounds here were -1 to 1, that was for x. Now we're in theta coordinates. So if x is going from -1 to 1, theta must be going from here to here, I guess. Wait. Sine. So sine's going from 0 to 0? No. Okay, so when x is -1, sine of theta is, I guess we could say from what, -pi to 0? Does this make sense? So square root of cosine squared is just cosine. I guess cosine's always positive here, so we can we don't have to worry about square root of cosine squared. That's just cosine, so it's just basically cosine squared. D theta, is that right? What if you change to 1 over x squared factors and split it into 2 integrals? How do I split it? I don't see how you would split it. I don't know how much easier I made this. This should be pretty easy to do. I don't know why I can't do this. I mean, this looks correct, but cosine squared, and then I always forget this. Is it the double angle formula or the -1 to 0 and 0 to 1? Oh. Yeah, I mean, yeah, you could split it again, sure. Yeah, we could do 4 times the integral from 0 to 1. Let's just do it that way. So from 0 to 1, I guess we're going now this way. So it should be from -pi/2 to 0, cosine squared theta d theta. And how do we do cosine squared as an integral? I think there's a way to rewrite it as like a, is it a sum? It's like, what is it? 1 plus 2 cosine, is it 1 plus or 1 minus? I think it's 1 plus 2 cosine over 2. Or cosine of 2 theta, I mean. I'm doing the most work to get. Yeah, that's what I had, right? Yeah, we're good. 1 plus cosine of 2 theta over 2. Thank you. Yeah, okay. And then we're doing the most work possible to calculate pi here. Okay, so now we can split it, so it's just an integral. Integral of 1 from -pi/2 to 0 times 4. So that's plus, or 1/2, I guess, so 1/2. Plus an integral from -pi/2 of cosine of 2 theta over 2 d theta. Hopefully we get the right answer. So the first one is an integral of 1, right? So a constant function, the integral is always just the length of how far you're integrating over, so that's just pi/2. so pi over 2 divided by 2. So that's pi over 4 times 4. So this first part's just pi. And the second part, antiderivative of is sine of 2 theta, and then we have to divide by the constant, so it's sine of 2 theta over 4. And then here it's the endpoints 0 and negative pi over 2. Yeah, and then at the endpoints, sine of 0 is 0, sine of pi is 0, so this is just 0 minus 0, so this is just pi. Oof. Okay, so 4 times the integral from here to here. I guess the easier way is to just do it in polar coordinates, right? I guess that's the way we should have done it, right? But this is more fun, right? So, yeah, so we took this area. It's the integral of square root of 1 minus x squared, where x goes from 0 to 1. Well, I guess we sort of did change to polar coordinates in some sense, right? Because we said, okay, no, let's change variables from x to theta. And now we're just going to do the integral in theta coordinates, and theta is going to go from this negative pi over 2 to 0, and now our function is basically just cosine squared here. So 4 times this area should be pi, and then we used our cosine squared formula to rewrite it with this 2 theta here. And then, yeah, this part's just 0, this part gives us pi, and that's... So that's what we would expect. Any questions? Yeah, I always forget this formula though. This one's annoying for me to remember. I don't know why. The cosine squared equal to 1 plus cosine 2 theta over 2. I don't know why it's hard for me to remember. Does anybody have any trig formulas that they, just can never remember themselves? Like, trig formulas can be pretty annoying, especially the cotangent derivative, cosecant derivative, stuff like that. Almost all of them are annoying, yeah. I agree. I hate the inverse ones. The inverse trig, like, derivatives are annoying. Like, what if you wanted to know the derivative of inverse cotangent or something, right? That would be, either you gotta memorize it or you have to rederive it each time, so not very fun. Yeah, I'm not feeling up to the research today. I'm just feeling the Pi Day vibes and not really feeling the research. You can also calculate dz over z over circle to get pi. Right, yeah, we actually did that a couple weeks ago. Yeah, we did. We've been doing some complex analysis for like Tuesday and Friday lessons, and yeah, that's actually one of the integrals we did. So in complex analysis, that also has pi, so I guess that's on topic. But yeah, that's a good integral, this closed line integral around the circle, boundary of the circle, dz over z. This one's actually 2 pi I. Right, but, obviously pi is showing up here because you're integrating around a circle, so that's not entirely a mystery, right? But yeah, that's another cool example. It's interesting you get an I out of this. I mean, it's not entirely unexpected. Oh, wait, I divided by dz. Oops. Not entirely unexpected though, because yeah, yeah, like I said, we're integrating around a circle, so clearly it has something to do with the length of the circle. That's where we're picking up the 2 pi. And the fact that we get this I here, that's interesting because we're getting this complex integral, but we're really just getting some imaginary parts. So all of the real part sort of cancels out, but the imaginary part doesn't. Yeah, over dz. No, just over z. Yeah. Typo. Yeah, so how would we compute this, right? So complex integral, we're going to have to parameterize it, right? So this is an integral from 0 to 2 pi of, now instead of dz, we're going to have a circle, so it's e to the I theta. But we want the derivative, so I can replace it with dt. So the derivative of e to the I theta is I e to the I theta. And then it's going to be divided by e to the I theta. So then these e to the I thetas cancel. You just get an integral of I dt. And that's how we get this 2 pi I. Simplest example of period? Yeah, that's it. Yeah, that's it. Literally. dz is on top, I e to the I theta dt, that's dz, and then z is on the bottom, e to the I theta, they cancel, you get an I. That's it, yeah. Yeah, I like this proof a lot more. There was a way to do it where you write it out with cosine and sine and like the real part and the imaginary part, but this way is like super simple. Yeah, so Kyler wanted us to do the similar integral, except not around the center of the circle. So like maybe you have a circle here and you want to parameterize the circle from the origin in polar coordinates, which I think is a very hard problem. Yeah, Euler made it simple with the Euler formula, of course. Yeah, we can celebrate E too. I wish there was an E day. I feel like E doesn't get the credit that it deserves, potentially. Although I think Pi Day is great because you can bring Pi to school, so that's probably why it took off, but who knows? Yeah, Euler is the ruler. All right, let me take a break for a second, and then I'll come back and do more Pi problems. But yeah, I just need a break for a second. All right, guys, I'll be back in, let's say, like 5-10 minutes. Good night. Hello. Hello, everyone. Happy Pi Day. Just been doing some pi-related problems on the board. Just gonna turn this down slightly. Yeah. So this was one of the integrals we've been talking about in the complex lessons that we've been doing on Tuesday and Friday. These closed line integrals, we were discussing this one integral. Usually these holomorphic one forms, they have a closed line integrals that are 0, but because of the singularity in this one form, dz over z, when you integrate it around a circle, you actually just get 2 pi I. So, unexpected pi result here. Usually, if you do an integral like this for a holomorphic function, like some function or holomorphic one form, so like dz, z dz, for example, has integral 0. Because it has a holomorphic antiderivative, in this whole interior of this circle, the integral is just 0. But this strange function does not. So, yeah. Do we have anyone following along that has any circle-related problems, probability-related problems, or anything with pi in it? Or e is okay too. Or an e to the I pi is especially good. I ran out of all my water. Oh no. Also, the product of all natural numbers is square root of 2 pi. Is that true? How do we get to that? I wish I'd prepared more pi-related problems. I was kind of just winging it, but I know, I said research in the schedule. It's my fault. I've been doing a lot of research lately. Calculate the derivative of zeta at 0. What is zeta? Like the Cauchy-Riemann formula zeta? Or, I mean, I'm not even going to attempt to do this, but there is a way to differentiate this equation. This is what we were doing last time, Cauchy formula. Also a pi, so counts. Riemann zeta. Calculate the derivative of the Riemann zeta function at 0. What is Riemann zeta? Is the sum 1 over n to the s, negative s, positive s? No, negative s, right? Yeah. Also, we have the Euler, product of over primes. What is it again? So you want me to take the derivative at 0? That's kind of difficult. I feel like I remember how to do it. I just don't remember it off the top of my head. What's this Euler formula again? I can't 1 minus p to the s? P to the negative s? Can't remember. I'm sure we could rederive the product formula, right? But yeah, I can't remember off the top of my head. But how do you take the derivative at s equals 0? Well, first of all, this function's not even, I don't think this function's even defined at s equals 0, or is it? Yeah, at s equals 0, it's just like 1 plus 1 plus 1 plus 1 plus 1, right? So you would have to do some sort of analytic continuation, I think, to even define this at 0. Or maybe the derivative is no. I think it has no, it doesn't have a pole, does it? In one hand, it's sum of logs of natural numbers, just checking the derivative over sum. In the other hand is negative 1/2 log 2 pi. Hey, Phobos. Yes, it's defined by analytic continuation. Yeah. But so we have a pole at s equals 1, though, right? That's the only pole. Or it's not the only pole, but is it the only pole on the real line? Or yeah, no. That's the only pole on the positive real axis, I think. So, and we know it's reflected about the real part of z is equal to 1/2. There's like this, the strip where all the interesting zeros are, right? On this imaginary 1/2 line. So I believe there's a pole here. There's like a blow up point at z equals 1. So I would assume there's also one at z equals 0, or no? Because there should be symmetry here, right? Happy Pi Day. Yeah, I don't know too much about Riemann zeta function. I've seen some of the arguments about, how fast the prime numbers grow, and, the fact that all the zeros lie on this line has some implications in that sort of department, but if you asked me to reproduce it on the board, I wouldn't be able to. It's a lot of like tough math stuff in there. So the zeros are here. There's also poles, I think, at the negative even numbers, if I remember. So like -2, -4. So yeah, I think there's also a pole at 0, but I can't remember. Pole at 0, pole at -2, pole at -4, pole at -6. Etc. Or are these poles or zeros? Maybe they're zeros. So yeah, guys, happy Pi Day. We're just fooling around a little bit with some Pi related stuff, some not Pi related stuff. Just, having fun doing math. Not really caring about much more than that today. Oh, yeah. So how's everyone in the chat doing? I'm just kind of wiped out. I've been doing a lot of my research math into the graph homology stuff, and very exhausting. So I was gonna go over some of it today, but I really have to get some of these proofs down. There's not really too much to say about it, so yeah. But yeah, the chatter that was talking about Riemann zeta, do you know how to find the derivative at 0 of the analytic continuation? I know the residues at 1 are actually important for number theory. So the fact that there's a pole at 1 and there's zeta functions for other number rings and other number theoretic type information, is stored in these types of functions, and the residue at z equals 1 actually tells you information about the number ring in general. So yeah, there's a big connection between these analytic functions, these zeta functions, these certain number rings, and I was reading something about like the Tate-Shevchevich group. I can't remember how to say it, but I never studied it. But you know, there's this like absolute Galois group acting on a field extension, and there's this whole like group cohomology story going into that sort of connection to like K theory and stuff. But that's not really the math I do. But I just thought it was interesting. I was reading about it the other day. Yeah, so I guess when my streams are less like fully focused, I know it's hard because the audience doesn't want to be like the driver of the stream, but yeah, I guess I wasn't super prepared today. But yeah, this is just a fun, Pi Day stream. Nothing too serious, but we've been doing some pi problems. During the lessons, we've been talking about Cauchy's integral formula, so this is something that's came up recently. This includes this 2 pi I in there. Yeah. I think I might end stream soon. There's, I'm just a little exhausted doing research all day, so. Any questions about Riemann zeta function that I probably won't know the answer of? Or Cauchy formula, or any other pi related questions we want to go over? I'm all ears, but yeah, kind of tired. So yeah, you guys let me know. Where's my water? Thank you, Phobos. All right. Good night, guys. Have a good Pi Day. Have a good rest of your weekend. It's Saturday. Let's see. Who can I raid?